Good day, everybody. So I'm going to talk about the mean meridional circulation today. So what is the mean meridional circulation? What am I talking about? So the mean meridional circulation is this circulation that goes north and south and it's a zonal mean circulation. And it's the circulation, large planetary scale, that sort of transports the heat and maintains the equilibrium on the planet. So it's not just circulation per se, but it's radiation in there, and it's a sort of dynamic equilibrium that it keeps going. So can you guys hear me? I'll try to talk. So I've picked this satellite picture. So while this looks like a bit of a dog's dinner, this is just a satellite picture from yesterday. Hopefully by the end of the talk, now I've done it. Oh, there we go. Hopefully by the end of the it looks a bit like a dog's dinner, but hopefully by the end of the talk, you'll be able to see some of the organization that's actually apparent in the satellite picture. Maybe. So what I'm going to talk about sort of introduce the topic, annual mean characteristics of the atmosphere relevant to the mean meridional circulation. MMC is mean meridional circulation. Then I'll talk about some of the developments that we've seen towards a theoretical understanding of the MMC. So this goes all the way back to the 16 and 1700s where this has been looked at. Then I'm going to switch tack, and that's sort of the academic part. Then I'm going to talk a bit about some of my research that I've been involved in at the Bureau. In particular, the tropical expansion and the changing MMC. And then if I have time, I'll talk a bit about an alternate view of the MMC. It's also an area of my research. So starting off with, first look at some of the annual mean radiative properties of the atmosphere or the planet. So the top is incoming solar radiation, insolation. And which one does the There we go. So the sort of annual mean is this solid line, and the seasonal means are the dashed line. So in the annual mean, the peak solar radiation is right over the equator. Sun shines brightest at the equator. It sort of varies with latitude as a cosine of latitude. Sun moves apparently in the sky with the tilt of the Earth. So during the summer or southern summer, DJF, the peak is about 20 degrees south, and the opposite situation in northern summer. So contrasting this with long wave radiation, it's fairly constant throughout the year and with latitude. So the infrared radiation is kind of constant around the planet. So when you do the net radiation, so the net balance, you see a net heating in the tropics, sort of to 40 south to 40 north in the annual mean, and then a cooling at the poles. And so this basic temperature difference is what drives the mean meridional circulation. So the circulation exists to try to relieve this disequilibrium. So the surface wind, again, this is annual mean from the ERA 40 reanalysis. And I've drawn some arrows to help highlight the flow, but what we see is sort of in the tropics, sort of 30 north and 30 south, we see some general easterlies throughout the year in the annual mean. And these are known as the trade winds. There's a sort of a lull in the winds, and then there's westerlies in the mid-latitudes. And then over the land, the winds are quite weak. Antarctica is a bit strange. There's lots of terrain and other things going on. So that's the sort of general structure of the atmosphere. Tropical easterlies and mid-latitude westerlies. And explaining that is part of what we need to understand with the theories of the mean meridional circulation. So looking at the latitude pressure view. So here's the southern hemisphere. And yes, I flipped it around deliberately because all my other plots, this had a different axis. So this is the zonal mean wind with height, pressure on the axis, northern hemisphere, southern hemisphere. So what we see in the tropics, we see these easterlies extend all the way up to 100 hectopascals. Again, these are the trade winds. There's a small patch of westerlies in the northern hemisphere, just north of the equator. And then in the mid-latitudes, we see the westerlies dominate. So these are the jet streams. This is the subtropical jet stream. And again, understanding why the subtropical jet stream is where it is part of what we want to get at with the mean meridional circulation. And then we also see what's connected, but they're separate when you look at them on a day-to-day basis, are what are termed the eddy-driven jets. So these jets are formed by the baroclinic waves. The baroclinic waves converge momentum into them and increase the westerly wind. And that increase in the westerly wind creates wind shear, which creates baroclinic instability, which creates baroclinic waves. And so there's sort of a symbiotic thing that goes on, that they're self-maintaining. They start, they converge the momentum, they change the atmosphere, and then they make more waves. And so that cycle keeps things going in the mid-latitude. So this is where the sort of the mid-latitude storm tracks will lie, where the cyclones and that sort of thing that cause day-to-day weather in the extratropics. Mean sea level pressure. So again, the features here. Near the equator, we see a general region of low pressure. And in the mid-latitudes, subtropics, we see a belt of high pressures that dominates. So this belt of high pressure that dominates is called the subtropical ridge. And there's one in each hemisphere. We see it's really centered on the western side of continents, but it extends all the way across in the B. And this low pressure near the equator is what's termed the intertropical convergence zone, or ITCZ. We also see a strong storm track of low pressure in the southern hemisphere, and that's, again, associated with that eddy jet. Precipitation. So again, precipitation is heaviest in the tropics. We see there's a lot of precipitation in the ITCZ all year round. Subtropical ridge has very low precipitation. This is the ITCZ. There's another South Pacific convergence zone here. Most of the precipitation, or a lot of the precipitation, is sort of confined to the maritime continent, West Pacific sort of thing. And this helps drive the ENSO, the El Nino, and all that, which you'll hear about in a few days. Finally, evaporation minus precipitation. So this is the difference. So where it's positive, this shows where there's evaporation dominates, and where it's negative, this shows where precipitation, positive is evaporation, negative is precipitation. So the yellows are the positive here. And we see in the subtropics, where the subtropical ridge is, evaporation dominates. It's much more comes out of the ocean than goes in. Precipitation dominates in the tropics, the equatorial tropics. Okay, so when we measure the mean meridional circulation, we usually use what's called a mass stream function. So you take the continuity equation in zonal mean, and you manipulate the equations, and you want to get this Stokes mass stream function, which is basically a vertical integral of the zonal mean meridional wind. So that's V in the vertical. And we want to solve this so that the equation, we get an equation for V and an equation for W, and we solve that to get the stream function here, which basically turns out to be an integral of this mean meridional wind. So what the stream function tells us, it gives us streamlines of the flow in the latitude pressure plane, or the zonal mean plane. So like isobars or any closer contours means a faster flow. So when we do this, we integrate the circulation, we get this strong circulation in the tropics. So around the orange colors, we have counterclockwise flow, and around the blue colors, we have clockwise flow. So we see a strong rising motion near the equator and a strong descending motion in the subtropics. And then we see two weaker cells out here. These are known as the feral cells, and they're sort of thermally indirect cells that form as well. And again, understanding this is part of understanding the theory. So this model is what's known as the three-cell model. So the Hadley cell, the feral cell, and then there are some weak polar cells as well that don't show up very clearly. So what this gives you is the mass transport within this plane. So it's strong upward motion near the equator and strong sinking motion. And these cells are known as the Hadley cells. When we look at this annually, so here's January through June, July. So we see this January, the upper motion is here in the southern hemisphere. We see one main Hadley cell, a weaker cell in the southern hemisphere. So this is southern hemisphere here. We see how this evolves during southern summer, DJF. The cell is mostly goes into the winter hemisphere. So it rises in the southern hemisphere near the equator and transports most of its mass into the northern hemisphere. And in the sort of the equinoctial seasons, there's sort of a balanced cell here. And it gradually reverses and overtakes so that the rising motion becomes strongest in the northern hemisphere and transports most of its mass into the southern hemisphere. And again, you see that. And it's just this cycle back and forth. And when we get to the equinox again, see again sort of a balanced presentation. So this plot kind of summarizes this variation. So the northern and southern hemisphere are quite different. So we take the edge of the Hadley cell on the subtropical side. We calculate the latitude that occurs at. We plot that on the y-axis here, and then the strength of this stream function, the maximum strength, which tells us how much mass is being transported through. And we see that sort of in southern summer, the cell is quite far north, but quite weak. And in winter, or another northern winter, the cell is quite strong, but more poleward. So the winter will be over here. So we see this sort of circle that outlines the strength and the intensity of the cell. You see sort of different behavior in the southern hemisphere, still stronger and more equatorward in the winter, and more poleward and weaker in the summer, but it's the variation in the southern cell isn't nearly as strong as it is in the northern hemisphere. Okay, so that's sort of the basic outline of the observations that we're trying to explain. So now I'm going to turn to the sort of more theoretical discussions, and I promise not to delve too deeply into this. But this is sort of how our understanding of the MMC has come about. So it's sort of 1686 was Sir Edmund Halley. So he's the guy with the comet and the astronomy and all that. So he's a pretty famous sort of guy, astronomy, calculating longitude, and he also introduced the idea of contour plots that we use so much today. So he took navigation charts that were recorded by seamen to keep track of the trade and when the best time to sail was and that sort of thing. And he put all those together and came out, and he was able to identify sort of what I showed before, what the mean flows were and how they varied seasonally and that sort of thing. And so from that, he was able to suggest that there was a thermally direct circulation with a return flow aloft. So what that means is there was rising air near the equator where it's warm, where it was cooler, you had sinking air, and then that made a large circulation cell. Sort of something like this. So Sir George Hadley, about 50 years later, so this is a pretty major advance. Sir George Hadley, again, 50 years later or so, he sort of introduced this idea that angular momentum had to be conserved in an attempt to explain some of the westerlies. And his language, he has the idea there. He doesn't call it angular momentum or anything, but he has the basic idea there. And so again, this sort of model he built on Hadley's work. He had this, again, they proposed this sort of model where it was rising air at the equator. It was one cell. It sunk at the pole. The air sunk at the poles. Yeah, so from this model, there should have been one area of precipitation near the equator and easterly winds everywhere. So obviously that's not quite right, but I guess what Hadley got at was the need for this momentum transport and the idea that there needs to be a balance in the momentum between easterly and westerly winds. So when we have near the equator, we have easterly winds, and the Earth's rotating in a westerly direction. So that implies that there's a momentum flux out of the Earth here. So angular momentum is being transported out of the Earth near the equator. And then further away, where we have westerly winds, the momentum flux is going the opposite direction, and it's going into the Earth. So there has to be a transport of momentum, angular momentum, between the equator and the pole to sort of balance the flow. If you don't have this balance, that would imply that the Earth has to slow down, or the atmosphere has to speed up continuously. So there has to be that balance, and we know that the days aren't getting shorter, and the circulation isn't speeding up out of control. So we know there has to be a balance between the momentum, and getting this momentum flux is a big issue in understanding the MMC. So that was all pretty good. That's a pretty good model for not actually having any, of what we would consider modern day observations. Hadley proposed the return flow aloft some 300 years before any upper air observations were even made. So to have gotten that and deduced that is pretty good. So that was kind of where things sat until the sort of mid-1800s. And then this American guy, William Ferrel, he independently introduced the concept of Coriolis acceleration to atmospheric science. So Coriolis had come up with the Coriolis stuff in the 1830s, working with machinery. Ferrel came up with the same idea and applied it to the atmosphere. So what he did was he hypothesized there had to be a second cell in the general circulation that rotated in the opposite direction to the Hadley cell. And that helped explain the westerlies that were observed. So here's an adaptation of his picture. So he has the easterlies converging near the equator and the Hadley cell rising and sinking. And then there's this second cell that is a thermally indirect cell that also circulates, that produces the westerlies in the extratropics. It turns out this Ferrel cell is sustained by the baroclinic waves that happen in the storm track. So that was sort of where things sat. Things swung back and forth. And so the early 20th century, so this is a paper from 1948, it swung around to the completely opposite view, and they said all the momentum transport is done by the baroclinic eddies, the mean meridional circulation, the axisymmetric zonal mean part. It's not important at all. It's all in the eddies. So it's, the importance of the Hadley cell and those circulations were completely diminished. That was sort of the case until so the late 70s and early 80s. So the sort of seminal paper here was Held and Hu in 1980. So they kind of built on these ideas out there looking at the axially symmetric circulations. And they came up with the theory that reestablished the importance of this Hadley circulation, the mean meridional circulation in general, for establishing, keeping the flow going. So this is sort of the seminal paper that explains the theory of the Hadley cell and what's going on. And I'll talk a bit about that. So Held and Hu, 1980, they had a simple idealized axisymmetric model. So axisymmetric means you have the axis and it's a sort of a zonal mean flow. It's a two-dimensional slice and it's the same everywhere around a hemisphere. So they forced their model. They said, okay, here's what the temperature looks like. We're going to perturb that, and then we're just going to let the temperature go back to its profile, its equilibrium profile. So that's how they forced their model. So the model conserves angular momentum and potential temperature. Very important. So what it turns out, that friction is actually required for the meridional flow in this model. When you don't have friction in the model, you just get a steady zonal flow, and there's no vertical motion, or no meridional motion whatsoever. So friction is required for the meridional flow. So what the theory ends up doing, it predicts the width of the Hadley cell, the total polar heat flux, the latitude of the upper level jet, the zonal wind, and distribution of surface easterlies and westerlies. So here's some figures from the paper. This is his stream function, and he shows the Hadley cell. He has it, sort of 30 to 45 degrees, terminating at about that latitude. So he's got the latitude about right. And he also has a strong upper level jet that's reminiscent of the subtropical jet, along with easterlies near the equator. And these are for different values of the friction parameter. And playing with the friction parameter changes a little bit. When he lowers it even more, he actually gets a bit of a ferrule cell into the model as well. So this kind of, that he can do this without any eddies or anything establishes the importance of the mean meridional circulation in establishing, maintaining the momentum balance on the planet. So he also came up with this scaling relation. So theta, or phi h, is the width of the Hadley cell, and it's sort of proportional to the height of the tropopause. Delta theta is the strength of the meridional temperature gradient, so that's the pole to equator temperature difference. The rotation of the Earth, the size of the Earth, and then the basic temperature. So the Hadley cell is wider for a higher tropopause, a stronger meridional temperature gradient. When the Earth rotates slower, the Hadley cell becomes wider. And when the Earth is smaller itself, the Hadley cell becomes wider. So what we have is the Hadley cell is actually sort of forced by the characteristics of our planet, how fast it rotates, how big it is, and that sort of thing. So there's some sort of undecided or unalterable characteristics there that help determine the width of the Hadley cell. Some other papers of note, and there's loads of papers written about the Hadley cell. It's probably one of the most popular topics that's actually out there. So Lindsay and Hu in 1988 used the Held and Hu model with the heating centered off the equator. So one of their criticisms was that the Hadley cell in the Held and Hu model was too weak, and didn't quite explain it well enough. So what they found is that when they displaced the heating off the equator, the circulation strengthened considerably. So this is what this figure shows. This is with the heating maximum right on the equator, and here you get two identically symmetric cells. When you shift it just 2 degrees off the equator, so the cells sort of towards the summer hemisphere, the winter cell that goes into the winter hemisphere becomes considerably stronger at the expense of the cell in the summer hemisphere. And when you splice it by as low as 6 degrees, basically the summer cell disappears, and you get quite a strong Hadley cell. So this is off the equator, you get a single solstitial cell that forms in the the southern hemisphere into the winter hemisphere. We call that the winter cell. And then there's not really a summer cell. So this is a pretty good idea. If we think back to what I showed with the annual variation, you do see some of that in there, but it's not quite as strong as what this model would predict. But there's some merit in this theory, I think. So finally, the last paper, and I won't go into this at all. This is Walker and Schneider, 2006. So what they did was they used an idealized GCM to investigate how the strength and meridional extent of the Hadley cell depends on the planet's radius, the rotation rate, and the thermal driving, the width of the, or the strength of the polar equator temperature gradient. So this is a really complicated paper. They do a lot of experiments, and it's kind of hard to follow. But if you want to really study this, you got to read this paper. So what they find is that existing theories of the Hadley cell are generally not adequate. What they find is generally the model flows, the flows in their model are generally in some in-between sort of state between the Held-and-Hu model and more linear theories. So it's neither one or the other. Both are sort of right in some situations, but they're not exactly right generally. So really the big conclusion they have is that the dependence of the Hadley cell on eddy fluxes of momentum, which themselves are dependent on extratropical circulation characteristics like the meridional temperature gradient, suggests that the tropical circulations depend on the extratropical climate. So the mean meridional circulation isn't just a tropical thing of the Hadley cell, but it really depends on the outside influences from the extratropics. So it's a global, hemispheric global sort of circulation as well. And that's, so we've kind of gone from not thinking it was all the eddies to think in Held-and-Hu were kind of it's all the mean or all the axisymmetric circulation. And now Walker Schneider, it's kind of a bit of both is what they're getting at here. So I've probably confused you. So I thought I would finish this section up with just what I hope is a plain sort of language discussion of the Hadley cell and what we see. So I kind of go through branch by branch here. So we'll start with the surface branch, and you can start at any branch. It's a circle, so you can start anywhere. So we'll just pick the surface branch to start with. So in the surface branch, generally from about 30 degrees in the hemisphere towards the equator, flows towards the equator. The Coriolis force shifts it so that it's easterly flow. These are what's known as the trade winds. So the surface branch flows from the extratropics towards the equator. It begins relatively dry out here in the subtropics. And then as it moves towards the equator, it moistens through evaporation on its equatorward journey. And this is the latent heat flux. So it's picking up, we're seeing that's where that evaporation is coming from. It's picking up moisture out of the ocean. So as it moves towards the equator, it becomes increasingly conditionally unstable with the addition of moisture. So then it gets to the equator. This is where it's in the intertropical convergence zone. So air from both hemispheres is flowing together here. Lots of convergence, plenty of stuff to release the conditional instability, plenty of lift. So this zone, where the rising branch of the Hadley cell is generally a zone of heavy precipitation. There's a lot of upward transport of heat, moisture, and momentum here. Latent heat release, condensation, water's condensing, raining out, releasing heat, heating the atmosphere, transporting it upwards. So what the rising branch is, it's associated with what are called hot towers. So these are the updrafts of individual convective cumulus clouds. So initially they were proposed that they take this undiluted air from near the surface and they transport it up into the Hadley cell, into the upper troposphere in the rising branch of the Hadley cell. And they calculated there needed to be sort of 1,500 to 2,000 updrafts at any one time on the planet to accomplish this necessary heat and transfer. And this was proposed in sort of 1958, sort of modified a bit in this 2009 paper. So one point that I think is really important, the rising branch is not this region of large-scale flow that forces convection. It doesn't work that way. Instead, it's the convection in the mesoscale that come together that produce this rising motion. So in actuality, near the equator, most of the time the air in the tropics is subsident. When it's clear, the air is sinking because it's cooling radiatively, so it sinks and it warms a little bit and it maintains that radiative convective equilibrium. And it's only when something comes along to force the circulation into the convection that you actually get the upward motion. And it's really not just any cumulus cloud. You know, if you don't have the proper environment, you just get a piddly little cumulus cloud that doesn't do much, and it goes up to 10 kilometers and it dies, and it doesn't transport much heat, and doesn't transport much of anything. It's only when you get the organized convective systems that you really get this Hadley cell circulation going. So, and this isn't a region of constant upward motion. It's the small scale influencing the large scale is what it is, rather than the other way. It's not a top-down thing, it's a bottom-up thing. That's a particular bugbear. So in the upper branch, the upper branch is sort of the outflow of this rising branch in the mesoscale convective systems. So it partially conserves angular momentum, and it does that by it adds westerly wind as it moves poleward. So I say partially. We know it's partial because if you took a parcel at rest at the equator, it would have to be going something like 150 meters per second by 30 degrees if it purely conserved angular momentum. So it doesn't purely conserve angular momentum. And that's where the eddies in the upper, which they kind of dissipate some of that energy and convert it into other forms of energy. But this upper branch, this ends in the subtropical jet because of the conservation of angular momentum. So what happens is the flow moves poleward and turns increasingly to the west, or from the west to the east. And then that's what forms your subtropical jet that we saw sort of at 30 degrees. That's the subtropical jet at those latitudes. So one theory has it that the subtropical jets occur where the flow becomes baroclinically unstable. So the jet gets strong enough that it creates baroclinic instability, and that breaks down the subtropical jet, and that's where the subtropical jets form. So the upper branch transports heat poleward, and then within the upper branch there's lots of radiative cooling to space. So finally, we have the descending branch of the Hadley cell. And again, it's strongly subsident. It is the descending branch. So this is, generally here is where we find the warmest and driest air, very low relative humidity in the descending branch. Strong radiative cooling happens here. It's clear, it's dry. The air can cool the space less impeded than it would be otherwise. And then what this ends in is the subtropical ridge in the lower troposphere. So you have the high pressure in the subtropical ridge around here, the low pressure near the equator, and that sort of drives the whole circulation in the Hadley cell circulation. So that's a sort of an overview of and discussion of some of the Hadley cell points. So now I'm going to talk a bit more, go into some more of my current research, climate change and that sort of thing. So in particular, I'm going to talk about tropical expansion. So what is tropical expansion? Again, generally, what we think of this is a poleward shift in this descending branch of the Hadley cell. It's moving poleward. So the Hadley cell is getting wider, or Hadley cell expansion, or tropical belt, width, the widening, and that sort of thing. There's different ways to measure the width, but the Hadley cell is a convenient way to visualize it. So CMAP 3 and 5 simulations show a shift or intensification of the subtropical dry zone. So this top plot shows CMAP 3 results. This is where there's a drying of the atmosphere in the models. So it's sort of 2 millimeters per day of drying by the end of the 21st century in the subtropical ridge belts with a moistening in the equatorial zone. So the dry areas get drier while the wet areas get wetter. So there's more precipitation expected in the equatorial zone. So this leads to more frequent drought and increased aridity at the surface. So, lots of people live in the subtropics. We live in subtropics. This is problematic, potentially problematic if we don't understand this. So I guess a bit more motivation. Why do we care about tropical expansion? And again, from an Australian perspective, so one of the things we've seen is from the 1970s, we've seen a strong decline in rainfall in Western Australia. So this is the rainfall deciles from 1997 to 2013, so sort of the lowest rainfall on record during that period. Closer to Victoria in Southeast Australia, we saw the millennium drought from 1997 to 2009. And again, seeing regions of the lowest rain on record. So it causes all kinds of problems. Tropics are getting wetter, subtropics are getting drier. So lots of impacts of this, water resources being a main one. How do you manage the water so that 4 million people can live in a city like Melbourne and still have water to drink? Agriculture impacts, fire weather impacts, more dry, more hot, more fire. And then it has lots of political impacts as well. You're fighting over what we're going to do with the desalinization plant and that sort of thing. So I guess the question that's motivated a lot of our research is this a sign of tropical expansion? This pattern certainly looks like it. Is this a sign of global changes to the mean meridional circulation having a local impact? What can we do about it? Can we predict it in the future? How can we provide water managers what they need for the future? So there's been numerous state-based climate initiatives to understand the causes, make projections, and help agencies manage these sort of resources. So that's where a lot of our research has been funded from. So one of the first things we've done is written a review paper about what the literature says about tropical expansion. There's lots of different ways to measure the edge of the tropics, as you will. You can use the Tropopause height. I'll talk a bit more about that. Satellite-based data, these sort of stream function studies, edge of the Hadley cell, positions of the jet stream. And then you can use surface-based features like where the rainfall is or where the surface pressure, subtropical ridge is, where the boundaries of P minus E are, and that sort of thing. So this diagram is a summary of all the literature to about 2013 that explains this. So the X's here are the northern hemisphere values that have been found by these different methods. The crosses are the southern hemisphere values. Vertical displacement doesn't mean anything. It's just to separate the plot, separate the symbols. So you see that studies with the tropopause, and when it's on the northern hemisphere side, that means an expansion for the northern hemisphere. So these are expansion, whereas if it's on the southern hemisphere side for the northern hemisphere symbols, it's a contraction. So it says that the tropics are getting smaller. So see a lot of variability in the Tropopause height stuff. Tropopause height says that some studies say that there's actually contraction in the northern hemisphere, but generally expansion in the southern hemisphere. Satellite-based studies generally show a stronger expansion in the southern hemisphere, stronger expansion in the northern hemisphere, but there's a lot of scatter in all the satellite-based studies. The reanalysis base edge of the Hadley cell kind of have a bit of a tighter range, sort of between 0.5 and 1 degree per decade trend. Jet streams have the smallest amount. They're highly clustered together, sort of about 0.1 to 0.2 degrees per decade of expansion. And then the other surface-based methods are all over the map, including one that says, you know, it's expanding at 2 degrees per decade. So I guess some of the questions here is the expansion equal in the hemispheres, or does one hemisphere expand more than the other? And which one is it in? Because different estimates give different methods. And it's just a consequence of different physics of how we measure these things, or there are other data issues, like this one that's out at 2 meters per second is probably a dodgy reanalysis or something. So it's not particularly reliable. So you need to take in data issues and methodology issues all into account. And these are sort of where this study lies now. Generally what we find, though, is a consensus of between, since 1979, about 0.5 degree to 1 degree per decade of expansion. So that's sort of 1.5 to 2 degrees since 1980, or thereabouts. So go a bit more into this. Again, how we do make some of these estimates. How am I doing for time? I better hurry. So Hadley cell, again, we can define the edge as a zero contour on the subtropical side. So here's your Hadley cells. So my colleague Han Nguyen did this for 8 reanalyses. She used this 3-cell model and defined the edge based on the zero contour. So what we found here is that these are the different reanalyses in the northern hemisphere edge and the southern hemisphere edge. So we see that the reanalyses are more consistent in the southern hemisphere. They're kind of all over the place in the northern hemisphere. Expansion again in the range, 0.1 to 0.8 degrees amongst all the hemispheres, and there's greater expansion in the warm seasons. What's really interesting is you see these sharp changes from 97, 1998. I guess there's a question of, is that a real phenomenon, or is that, they changed the observation system that affected the reanalysis? And I think it is kind of probably something that's at least partially real. Tropopause Height Frequency method. So again, we can use tropopause statistics to determine the edge of the tropics. So we look at 2 stations. This is 4 years worth of tropopause height data daily for Charleville and Cobar. These are about 500 kilometers apart in eastern Australia. We look at Charleville. The tropopause is always sort of between 15 and 17 kilometers the vast majority of the time, whereas in Cobar, sort of in the summer season it's high, and in the winter season it's more low. So we can use this difference in the distribution of the tropopause height to identify where the edge of the tropics is, contour this array, and then we can get some estimates of tropical expansion. So I've done this globally for certain regions for all the radiosonde data. So we've done this on a regional sort of scale, looking at the regions defined by the box. The dashed lines are sort of where the subtropics are, where the variability, or where the boundary lies. So what we see is when we look at this regionally, we see most of the expansion is occurring sort of in the Asia region and the Australia, New Zealand region. That's where it's quite strong. Again, that's where the sort of the main area of upper motion in the atmosphere is. That's where all the precip is. Further afield, we see 0.2 to 0.3 degrees, 0.4 to 0.5. Significant in all these regions, except in North America, where we see a 0.2 to 0.3 degrees per decade expansion, but it's not actually statistically significant. So what we've done is we've looked at the variation of these with different teleconnections, these climate variability. So we see that INSO strongly affects and accounts for 10 to 30% of the trend. So since 1979, there's been an apparent trend in INSO towards more La Nina states. And that La Nina states mean a wider tropic. So that accounts for maybe 10 to 30% of the trend. In Asia, what's going on, the Pacific Decadal Oscillation accounts for about 50% of the trend. So when you take these effects out, we get a more uniform value of sort of at the lower end of the range, sort of 0.2 to 0.3 degrees of expansion. So that kind of helps to unify this view that the tropical expansion isn't that much, and it's been other factors, external factors, the PDO and INSO and SAM and things like that, that have accounted for a lot of the expansion that we've observed over that time. So this difference brings it much more into line with what the CMET3 models say for the predicted expansion. So briefly, factors behind tropical expansion. Modes of climate variability explain some portion of the trends and help resolve uncertainty between models and observations. Some of the other forcings that have been proposed for tropical expansion, simply greenhouse gas. Again, it's a change in static stability and leads to a weakening in the Hadley cell, and that causes it to expand a bit. Stratospheric ozone depletion. There are many studies out there that suggest this is the sole or main driver in the southern hemisphere. So we might expect more expansion in the southern hemisphere here. Aerosol and tropospheric ozone, particularly in the northern hemisphere. And that's kind of a weak forcing, but persistent. And then there's a natural forcing that volcanoes in particular can act to contract the tropics over the short term. But that's sort of a 2 or 3 year thing. But again, if you start your trend calculation at the wrong time relative to the volcano, you can get an apparent trend that's not reflective of reality. It's a danger of using short time series. So briefly, I'll talk about isentropic streamfunction. So this is sort of computed in the same way as the other stream function, except we do it with potential temperature as a vertical coordinate. So we calculate a stream function, use the mass flux, calculate a stream function from that. And here we get a bit of a different picture of the view, I should say. In this view, it's not strictly geometric. It's not geometric in height. It's temperature. So here's the tropopause. This is purple line. And then this red line is sort of median surface temperature. So that defines the surface, and that defines the top of the troposphere. So what we see is this diagram is interpreted the same way, counterclockwise around orange, clockwise around blue. You see strong rising motion near the equator. But then instead of the Hadley cell cutting off, we see this interaction with the tropics, or with the extratropics and the tropics. So we can see our Hadley cells here. This is sort of the Hadley cell part of the flow. And then we see this extratropical mode, which is also important, which wasn't as emphasized in the pressure coordinate view. So this is your polar front circulation. So transporting cold air towards the equator and warm air polar, or towards the poles. So from this we can, here we go. So we see the flow sort of goes as outlined by the arrows. So we see a single hemispheric cell that takes in both the extratropics and the tropics. Looking at it seasonally, we see quite a bit of that solstitial type behavior. Strong cells in the summer, strong cells in the winter hemisphere, weak cells in the summer, and sort of but not quite solstitial, sort of a balanced view in the equinox seasons. Yeah, we put this together, come up with a sort of idealized model showing what's important for the Hadley cell. So it's important for the MMC. Again, here's our Hadley cell, ends in the subtropical jet stream, descending motion, subtropical ridge. And then this connects in with the polar front. The polar front variability is affected by the annular modes. There are storm tracks, the anti-jet stream. Stratosphere is really important. I haven't talked about it here, but the ozone hole is an important factor. talk about that. We can take this, we can divide this. One of the advantages of this, we can take this circulation, the full circulation, this is for DJF, and we can split it into sort of a steady mean flow part, and this defines our Hadley cells really clearly. And then we can have the extratropical or the transient part, which reflects the baroclinic waves more clearly. And we see two strong transient circulations in the extratropics with the Hadley cell circulation in the tropics. So from this, we can define our Hadley cell. We can look at the ITCZ and see how it varies in position and intensity, as well as the downward cells, downward branches of the cells. Look at this sort of mid-troposphere. For the southern hemisphere, we see a general expansion and intensification of the Hadley cell branch. See an intensification of the ITCZ, but no real change in position. And then we see a much more variable response in the northern hemisphere, where in JJA we see a strong expansion, but in the other seasons we see a much weaker expansion. In JJA, we see an actual weakening of the downward branch, whereas in the winter hemispheres we see a strengthening of it. Whereas in the southern hemisphere we see the strengthening in all seasons. So, what we got here? These are trends. So you see northern hemisphere is in blue, southern hemisphere is in green. Stars, the symbols are significant. So see sort of in summer and autumn in northern hemisphere is where we get significant trends.